Welcome back to The Explainer. You know, we all rely on internal combustion engines every single day, but we rarely stop to consider the extreme, totally unseen forces battling it out right under the hood. Today, we're examining a recent study investigating exactly how the heart of a car's engine handles unimaginable stress and how new materials science might just stop it from cracking.
Okay, let's dive into this. Because think about it, the internal combustion engine is basically the ultimate high-stress environment, containing millions of literal explosions, dealing with searing heat, and enduring intense pounding pressure. It pushes even the toughest cast alloys to their absolute limits, and eventually, that causes them to crack.
Here is our roadmap for today's study. We'll start with 1. The engine's breaking point. 2. Meet the contenders. 3. The virtual stress test. 4. Structural integrity results. 5. The heat flux factor. And finally, 6. The final verdict.
All right, part 1, the engine's breaking point.
So, the component taking the absolute brunt of all this punishment? It's the cylinder head. Sitting right there on top of the engine block, it houses the valves and spark plugs and helps seal the cylinders to maintain compression. It's the literal sealing of the combustion chamber, keeping all that pressure locked in.
Now, according to the source material, there are a few main culprits when these things fail. Modern cast aluminum alloy heads are highly susceptible to thermomechanical stress. Basically, you've got a constant barrage of over-temperature conditions combined with transient vibration. And eventually, that just leads to material fatigue and cracking. Not good.
Moving on to Section 2. Meet the contenders.
In one corner, representing the current industry standard, we have the cast aluminum alloy A356. And the challenger proposed by this study? A 7000 series alloy called aluminum 7D68. Now, if you look at their baseline stats, things like density, Young's modulus, Poisson's ratio, they're practically identical. I mean, they weigh the same, they share a very similar stiffness, but there is one glaring difference. And that crucial gap is in the yield strength. The current standard, A356, handles about 234 megapascals, but the challenger, aluminum 7068, it boasts a staggering 700 megapascals. It is almost 3 times as strong on paper. But hey, we need to see how it actually performs inside the pressure cooker of the chamber, right?
Which brings us to Section 3, the virtual stress test.
So, how do we test this without blowing up physical engine blocks? Well, the researchers used finite element analysis, or FEA. It's essentially a virtual crash test for molecules. By taking a 3D model, dialing in specific material properties, and simulating loading scenarios in software like ANSYS, engineers can safely subject the geometry to totally extreme digital forces.
The methodology here was pretty straightforward. First, they built a precise 3D model of a 4-cylinder head in SolidWorks. Next, they imported it into ANSYS, applied their intelligent meshing algorithms, and finally ran the structural and thermal stress simulations. If you look at the model, you can see how applying that intelligent mesh fractures the continuous geometry into thousands of tiny elements. It's kind of like a giant digital puzzle. This lets the computer precisely calculate how force and heat actually transfer from one finite element to its neighbor when it's under load. All right, Section 4, Structural Integrity Results.
Now, what's really interesting about this slide is the total deformation heat maps. We can see exactly where the metal warped. Notice those high-stress yellow and red zones? They're blooming right around the circular combustion chambers where the valves sit. That right there is the primary failure zone.
So, when subjected to an identical equivalent stress, right at 14.185 megapascals, these materials reacted very differently. The A356 showed higher total deformation and elastic strain. Meanwhile, the 7000 series aluminum held its shape significantly better. It literally proved it has superior structural integrity under the sheer physical pounding of combustion.
Let's pivot to Section 5, the heat flux factor.
Now, the thermal simulation actually revealed a really interesting, kind of counterintuitive data point. The proposed aluminum 7068 experienced a temperature distribution about 4.15 degrees Celsius higher than the old material. And I know, running hotter might sound like a bad thing at first, but it actually sets up a major victory for the new material.
Check this out. Despite that higher localized temperature, AL 7068 achieved a total heat flux of 0.07872 watts per square millimeter.
So what does that actually mean? Well, this superior heat transfer rate means the 7000 series pulls that extreme thermal energy away from the combustion chamber way more efficiently. It essentially acts as a super effective conduit to dissipate all that heat.
And that brings us to Section 6, the final verdict.
So, looking at the big picture, the study's results are crystal clear. Aluminum 7068 is absolutely structurally superior. It resists deformation far better than the current standard. On top of that, it offers a better thermal heat flux distribution, actively moving those damaging temperatures away from critical areas. Basically, swapping to a 7000 series aluminum alloy is a highly viable, realistic solution to drastically reduce cylinder head failure.
Not only did this study pinpoint a much better alloy for modern engines, but it really highlighted the incredible power of FEA. Think about it. Without melting a single actual piece of physical metal, we've definitively proven a safer structural path forward. It makes you wonder, as this software continues to advance, how will virtual simulations like this reshape the invisible engineering in the machines we trust our lives with every single day? Something to think about. Anyway, thanks for joining me on The Explainer.